Welcome to The Explainer. Today, we're diving deep into a fundamental but maybe overlooked part of software, how we encode our data. We're going to see how the choices we make today about something as simple as a data format have this massive ripple effect on our ability to change, adapt, and grow our applications tomorrow.
You know, the ancient Greek philosopher Heraclitus obviously wasn't talking about software, but wow, he might as well have been. This quote right here, this is the core challenge for any software engineer. Your application, its features, the data it stores, it's all in a constant state of flux. So the real question is, can your system actually handle it?
So here's our game plan for this explainer. We'll kick things off with why change is so tough. Then we'll explore the main kinds of data formats, uncover the secret weapon of schemas, learn how to use them to evolve things safely, and then wrap it all up by seeing how this applies in the real world.
Okay, let's get right into it. Our journey starts with this fundamental problem. See, in any big system, you can't just flip a switch and update everything at once. You do rolling upgrades. And that means, for a little while, you've got old and new versions of your code running side by side. So, how do you make sure they can still talk to each other? How do they understand the same data?
Well, the solution comes down to two key ideas. First, you've got backward compatibility. That's making sure your shiny new code can read old data. Honestly, that's the easy part. The real trick, the hard part, is forward compatibility, making sure your old code doesn't just fall over and break when it sees data from the future, written by your new code.
Okay, so now that we know our goal is compatibility, let's explore the whole landscape of data formats. Think of it like we're on a journey across this huge continent of encoding options, and every region has its own unique benefits and its own dangers.
And here it is. This map from the source material just brilliantly illustrates the world we're exploring. Over on one side, you have the coast of textual encodings, with familiar places like JSON and XML. And on the other side, the gulf of binary encodings, a much faster but definitely more complex territory to navigate.
Let's start our journey on that southern coast. Formats like JSON, they're super popular, right? Because we humans can read them, but they come with these hidden problems. Numbers can be ambiguous. Binary data has to be awkwardly crammed into text, which bloats its size by a third, a whole 33%. And since schemas are optional, you end up hard-coding all this messy logic into your application just to figure out what the data means.
All right, to make this really concrete, let's take a sample piece of data, say a user profile. It's got a name, a favorite number, and a list of interests. If we encode that in standard JSON, it takes up 81 bytes. Okay, remember that number, 81 bytes. That's our baseline.
Now we can try to do better by sailing into that gulf of binary encodings. Message pack is basically a binary version of JSON. And yeah, it shrinks our record down to 66 bytes. That's better, but it's not exactly a game changer. And why is that? Well, because it still has to spell out the full field names, username, favorite number, right there in the data itself.
To get some real efficiency, we need to leave the coast entirely and travel inland, along with the map calls the road of schema. A schema, which is just a formal description of our data structure, turns out to be our secret weapon. This slide right here shows you the power of a schema in action. With a format like Apache Thrift, instead of using text field names, we use numeric tags. So favorite number just becomes tag number 2. And just look at the difference. The basic binary protocol gets us down to 59 bytes, but their compact protocol, which uses some clever tricks for packing numbers, gets that same exact record down to just 34 bytes.
And if we push even further, we find the real champions of compactness. Google's protocol buffers is a lot like Thrift, and it gets our record down to 33 bytes. But then there's Apache Avro, which goes one step further. It's so efficient, it doesn't even need to include the field tags in the data, getting us down to an incredible 32 bytes.
So here it is, the payoff of our whole journey, all in one place. By moving from a simple textual format like JSON to a schema-driven format like Avro, we've cut our data size by over 60%. We went from 81 bytes all the way down to 32. I mean, that is a huge saving when you're working at scale.
But here's the crucial point. These schemas are not just for saving space. Their real power is that they give us a compass for navigating that whole challenge of change we started with. They are the absolute key to evolutionability.
So in Thrift and protocol buffers, these field tags are basically magic. Let's say you want to add a new field. You just add it to your schema and give it a brand new, totally unique tag number. Now when your old code reads data written by the new code, it sees a tag it doesn't recognize. And what does it do? It just skips it. It knows exactly how many bytes to jump over because the data type is encoded right there. And just like that, forward compatibility is solved. Now, Avro uses a different but just as powerful kind of magic.
It decouples the schema used to write the data from the schema used to read it. When you read the data, the Avro library looks at both schemas, the writers and the readers, and it translates the data on the fly by matching fields by name. So what does that mean? Well, if a field is in the writer's schema but not the reader's, it's just ignored. And if it's in the reader's but not the writer's, a default value is used. Pretty cool, right? So let's bring it all together. Using a schema is a massive win for so many reasons. You get much smaller data, which saves you money. The schema itself acts as perfect, always up-to-date documentation. You can even write tools to automatically check if a schema change is going to break compatibility before you ever deploy it. It gives you this whole toolkit for safely evolving your system over time.
All right, let's move to our final section and see how all these principles actually apply to the different ways data flows through a real-world system. Because it's not just one flow, right? It's a whole network of rivers and streams.
When data flows into a database, you have to remember this critical rule. Data outlives code. A record written 5 years ago by some long-gone version of your app still has to be readable today. You can really think of a database as sending messages to your future self, and that makes forward compatibility absolutely essential. But this also shows a really common trap. Imagine your new code adds a photo URL field to a user record. Okay, great. But then an older version of the code reads that same record to update, the favorite number. The old code has no idea what a photo URL is, so when it writes the record back, boof, the photo URL is just gone. You've actually lost data, and this is exactly why preserving unknown fields is so incredibly important in a read, update, write cycle.
And of course, these exact same principles of compatibility apply literally everywhere data flows. It doesn't matter if you're building services in what our map calls the People's Republic of RPC, or you're sending events through the mountains of message passing, that need to manage change and evolution is constant. The sender and the receiver have to be able to understand each other, even if they're totally different versions.
Ultimately, your choice of data encoding is foundational. It's not just some technical detail. It's a decision you're making about the future you're trying to build. So you have to ask yourself, are you choosing a language that's rigid and brittle, or are you choosing one that's flexible, resilient, and ready for the one thing we can always count on: change?